Welcome to this session on subsurface utility engineering, detection and mapping of underground utilities. This is session 1, in which we will be talking of basics of SUE, giving the fundamental process of subsurface utility engineering. I am Sanjay Rana. I am a geophysicist by profession, working in the field of near-surface geophysics for last 28 years. I have been working with subsurface utility engineering using the appropriate tools like ground penetrating radar, induction locators, etc. for last 20 years. In this particular presentation, we will look at what is SUE, why use it, how does it work, what are the basic data processing steps, what do we mean by subsurface utility maps, what is the typical team structure of a SUE team, and conclusions. So I would like to take you through a video which beautifully captures the entire process of SUE. The video has been taken from USA, but it is applicable practically to all the situations in the world.
Have you ever been involved with a construction project that encountered utilities that nobody really knew were there? I'm sure that's happened to just about everybody that's worked in the highway industry over the last quarter century or so. Hello, I'm Bill Wiesman, Director of FHWA's Office of Engineering, and I'm here to introduce you to a video that will describe a proven new process for taking care of this age-old problem. The solution is called subsurface utility engineering, and it indeed is a proven solution to this problem, and it will help us ultimately save time, save money, and produce a better product for the American tax-paying public.
Virginia Department of Transportation has been applying subsurface utility engineering to its transportation projects for over 10 years. We have documented savings of $7 for every $1 spent to locate potential utility conflicts.
We estimate that we save $18 for every dollar spent on subsurface utility engineering.
In Pennsylvania, the project owner can be held legally responsible for the accuracy of the information on the bid documents. Consequently, we want a competent professional to obtain that information for us.
Subsurface utility engineering values have gone far beyond the documented dollar savings. It's really meant keeping our projects on schedule.
We have tremendously reduced the risk of delay claims, extra work orders, damages to utilities on projects where we've used comprehensive subsurface utility engineering.
What is subsurface utility engineering? Quite simply, it is a proven process that incorporates new and existing technologies to accurately map underground utilities during the development of future construction projects. It encompasses several separate activities, including designating, locating, surveying, and mapping, all of which are performed under a professional program of data management. The essence of subsurface utility engineering is simple. Before an engineer designs a project involving excavation, the engineer should know what structures and conditions are beneath the earth and where they are in 3 dimensions. Such structures are usually utilities, but may include underground storage tanks, septic fields, and other things. Before the development of subsurface utility engineering, the standard methods to determine the location of underground structures were inefficient, risky, and costly. Today, because of the availability of subsurface utility engineering, both horizontal and vertical locations are available quickly, accurately, and inexpensively.
Subsurface utility engineering is the answer to many of our utility problems.
Subsurface utility engineering involves the collection of underground utility data and the use of that data by the right parties at the right time. Its major components, designating, locating, surveying and mapping, and data management, can be defined in terms of quality levels of information. Quality levels may be thought of as degrees of risk, or how much information is really needed before planning, designing, and constructing a project. There are 4 quality levels. Quality level D is the most basic and the least desirable level of data. It comes solely from available utility owners' information. It has application for planning purposes such as selecting routes and estimating utility relocation costs. Even though quality level D information may provide an overall feel for the congestion of utilities, it is highly limited in terms of comprehensiveness and accuracy for design purposes.
In Maryland, we have used quality level D since 1988 in the planning phase of our projects. This is usually adequate for route selection. But make no mistake, this level of data is not adequate for design purposes.
Historically, quality level C was probably the most commonly used level of information for design purposes. It involves supplementing quality level D information with an above-ground survey of visible utility features, such as manholes or valve boxes.
Looks like they've paved over the valves.
But utility records and topside survey data are just not enough to provide an accurate picture of where subsurface utilities are located. Professional studies have shown a 15 to 30% error or omission rate with this approach. So quality level C should rarely be used for design purposes when underground utilities are present. Quality level B is the first level where subsurface utility data departs from traditional practices. It involves supplementing quality level D information with designating, surveying, and mapping. Designating is the use of surface geophysical prospecting and remote sensing technologies to determine the existence of underground utilities in plan view. The use of this information allows decisions to be made during the preliminary design phase of a project on where to place storm drainage systems, footers, foundations, and other design features in order to avoid conflicts with existing utilities. Slight adjustments in the design can produce substantial cost savings and increase safety by eliminating utility relocations and moving excavation work away from existing utilities.
A total of 66 feet from that offset.
Quality level B data is invaluable in designing our construction input. It also provides quick access to data during an emergency.
Quality level A information is the highest level of accuracy currently available. It involves adding locating to the quality level B information. Locating is the exposing of buried utilities to determine how a state or municipal public works agency engages a subsurface utility engineer may be as important as whether they engage one at all. Why? Because inaccurate subsurface utility data is probably more dangerous and inefficient than none at all. A registered staff professional must review subsurface utility engineering data and deliverables. He or she must seal the appropriate work product and be individually and corporately responsible for the accuracy and reliability of the data delivered. With no professional review or sealing, no one is responsible for the information. Remember, accountability is the key. Professional liability insurance that underwrites a provider's operations is essential. The claims record of the provider is also important, since it is indicative of the quality of that provider's services. Without professional liability insurance, there may be no money to back a provider's accepting responsibility. Specific written quality assurance procedures that are applied to each and every project also are critical. Without written procedures that are universally applied, the data may not be accurate or reliable. Procuring agencies should specifically review these procedures and insist on their use. Subsurface utility engineering is an interpretive science. The amount of experience a provider has is directly related to its ability to interpret the wealth of information that goes into a subsurface utility engineering project. The more experienced the provider, the less chance for misinterpreted data. No one piece of equipment can provide all necessary subsurface utility engineering data. So a provider needs to have experience in a wide range of equipment and their application to different project conditions, configurations, and so forth. A subsurface utility engineering provider must be able to work within an agency's specific CAD requirements. Experience in different systems and particular experience in a specific system will improve a project's efficiency. Subsurface utility engineering is often applied when project schedules are tight. Check your provider's record of timely performance. Remember, time is critical when you are trying to get your project out to bid. Subsurface utility engineering is multifaceted and draws from many areas of expertise. A provider must have multiple disciplines at its disposal to address the multitude of problems confronting a project. At a minimum, geologists, surveyors, and engineers are needed. Bottom line, untimely and inaccurate utility information is often worse than no information at all. Agencies need to take the lead in the procurement process to assure they get the best quality services at fair and reasonable prices. Many ask, why should an agency pay for these services when utility companies may be legally responsible for the information? First, it is the agency's project, and they should take responsibility for the information you need.
Utilities find it difficult to respond to our project schedules. By MDOT contracting these services, we get the control, accuracy, and timeliness that we desire.
Highway agencies and utilities both benefit from using subsurface utility engineering. In many states where it is being used, the highway agency pays for it, generally as a preliminary engineering activity. But in a few states, the utility pays. And in some states, the highway agency and utilities share the cost. No matter who pays, the party with the greatest incentive for getting timely and accurate information should retain control over the subsurface utility engineering work.
We have considered using utility companies to locate and designate their facilities, but we found that this is just not practical or cost-effective. On this issue, we could not justify spending a dime of administrative cost to receive a nickel's worth of value.
Subsurface utility engineering is not limited in its application to roadway projects. In fact, getting accurate and reliable subsurface utility data is appropriate whenever there is a significant likelihood of a backhoe, piling, or anything else conflicting with an underground utility.
It's especially beneficial to have accurate utility information at the start of design to avoid future utility relocations and their associated costs.
Apart from all the other good news about subsurface utility engineering, consider this. When you apply it, you get lower bids.
On one job, we applied it, and our bids were $400,000 lower than we anticipated.
CH2M Hill uses subsurface utility engineering on a wide variety of our projects, involving such things as water, wastewater plants, environmental remediation, and the wide range of our transportation infrastructure. We find that subsurface utility engineering provides both value and quality to the type of work that we do for our clients.
In the past few years, you've seen on the evening news the effects of excavation damage to pipelines and other buried systems, impacting the environment and public safety. Many of these incidents are the direct result of poor information on the location of those systems. At the National Transportation Safety Board, we're promoting subsurface utility engineering for one reason and one reason only. It protects pipelines, the environment, and most importantly, people's lives.
From an academic perspective, subsurface utility engineering just makes sense. You're able to shift the risk that's involved in the engineering and construction process of bad information to the party that's most able and qualified to accept that risk, and of course that party being the subsurface utility engineer.
Subsurface utility engineering applies anytime excavation will occur around underground facilities. Subsurface utility engineering saves time, money, and lives. Together, as leaders in the engineering, construction, and utility fields, we can improve schedules and lower project costs. Spread the good news about subsurface utility engineering. It's a proven solution.
Alright, so this video basically captured the entire process of subsurface utility engineering, which is a great starting point. Now we'll talk about certain basic concepts of SUE. The code which has been developed and followed mostly around the world is a comprehensive code by American Society of Civil Engineers, ASCE 3802, and in this particular presentation we will be talking mostly through this code. First of all, the importance of SUE comes from the fact that the footprint of new construction, repair or remediation often conflict with existing infrastructure. We have seen this particular phenomena more often than not, that as we start the construction, that's the time we find out about underground utilities with pipes and cables and things like that. Now, this infrastructure, when it is detected in the construction phase, that's most often the situation. But cost of conflict resolution and potential for catastrophic damages are highest at this stage. You can understand, the entire construction machinery is there, personnel are there, we are ready to execute the project, and suddenly we know that there are underground utilities which needs to be taken care of. So by the time we are able to do that, the complete infrastructure comes to a halt. It's on standby and the cost is very high. Talking about damages, catastrophic damages, there have been number of cases where an underground, for example, a gas pipeline has been hit during the construction process, resulting in loss of equipment and even life. So inaccurate, incomplete, outdated information on existing utilities reduces the engineers, owners and contractors' ability to make informed decisions and to support risk management decisions regarding the project's impact on existing utilities. So ultimately, what we are doing is we are taking the decision mostly with our eyes closed, with very limited information. And of course, a person like this cannot call himself a smart decision maker. So SUE basically is new technologies for solutions, that is surface geophysics, surveying techniques, CAD and GIS, minimally intrusive excavation, convergence and systematic use of this data. This entire process comes to be called as subsurface utility engineering. Down to the basics, SUE basically establishes credible nomenclature system to fix attributes to utility information to denote quality of utility information. It's very important to understand this point. If you look at the maps which generally come to us from any authority, they will show utility in different manner. For example, the old archived maps can be simple ammonia prints showing utilities by maybe a sketch pen in red color or green color or brown or whatever, showing different kind of utilities. Now the same maps sometimes are digitized. Now that's where the problem starts. Till the time this map was coming in the simple, ammonia print format, no one was confusing this map as an accurate depiction of the position of the utility. Rather, everyone knew that it's just a schematic showing that utility might be present somewhere on this particular road. But when we digitize the map and give a CAD output, putting the utility either in the center or the side of the road, and give this output to the data user, he gets a feeling that this map has been prepared based on some input data, which actually was never there. So the maps which we receive today do not give us any indication of the quality of the map, the information by which it has been generated, and how much we can actually rely on it. This is what exactly SUE does. It basically gives a nomenclature system which on any particular map generated by the process of SUE tells you what is the level of confidence you can have in different utilities which have been denoted there, which have been depicted there. So the standard which is there for SUE deals with how information can be obtained, what technologies are available to obtain that information, how that information can be conveyed to the information users. The intent of the entire process is to reduce risk by improving the reliability of the information on existing subsurface utilities in a defined manner. There are certain definitions which are important to understand when you talk about SUE. Because more often than not, when we are doing a geophysical investigation using things like a GPR or induction locator, we very commonly use the word we are locating a underground utility. Well, if you go strictly by the standard and the nomenclature, the word for that is designating. So geophysics for presence and approximate position of utility, that's what we call designating. When we come up to locating, it is exposing and recording precise vertical and horizontal location. Now this exposing and recording, we will see later, can be done by vacuum excavation, it can be done by careful hand excavation, but we call locating only when we are actually exposing and recording the precise vertical and horizontal location. Another definition is minimally intrusive excavation. This is vacuum excavation, water jet, careful hand tool uses, etc. Then subsurface utility engineer. This is a person who by education and experience is qualified to practice subsurface utility engineering. Utility depiction is a visual image of the existing utility information using a computer-aided design and drafting system or on project plan sheets. And most important, utility quality level. This is the backbone of the entire process, where each utility is given a quality level which gives opinion of quality and reliability of the utility information. So once we talk about the quality levels, there are 4 quality levels which have been defined in ASCE 3802. There are other standards also which further bifurcate these quality levels, but for this discussion we are restricting ourselves to ASCE 3802. So quality level D is the information gathered solely from existing utility records. Quality level C involves surveying visible above ground utility facilities and correlating this information with existing utility records. Quality level B is where the significant advancement has taken place in terms of the mapping of underground utilities. It uses surface geophysical techniques to determine the existence and horizontal position of underground utilities. So here comes your geophysical surveys part, and then the final quality level, that is quality level A, employs non-destructive digging equipment at critical points to determine the precise horizontal and vertical positions as well as size and type of underground utilities. These are the guidelines which are ASCE standard guidelines for collection and depiction of existing subsurface utility data. These are guidelines. Of course, depending on where you are practicing SUE and the unique nature of utilities and record keeping, it might necessitate various changes in the SUE approach. So, why use SUE? Well, the answer is that we don't know where most utilities are, and honestly, there are plenty. If you actually cut open the underground, you will see there is a jungle out there. And unfortunately, there are plenty of utilities and they are not organized very well. So this is the kind of scenario which you can see if you are looking at a subsurface condition. So we don't know where most utilities are. Existing records are often inaccurate and incomplete, and risks become extremely difficult to manage. And what are these risks? Project delays, damage to utilities, safety of workers, safety of public, redesign costs, change orders, bad publicity. So these are the risks which are very difficult to manage unless we are able to collect a good data on underground utilities. Third party damages, you can see if there is an existing pipe and you do not know the location of this and you are going by, let's say, horizontal direction drilling, you have all the chances of hitting the pipe, and these kind of risks are difficult to manage. So how does it work? First of all, SUE doesn't follow any set pattern. There is nothing that this is exactly the pattern which has to be followed for SUE. There are guidelines. You have to go, for example, in the increasing order of accuracy, that is, the higher quality levels are to be done, but you have the flexibility to make modifications depending on where you are working and what is the requirement of the project. So it is tailored to individual projects. It essentially involves systematically identifying the quality of utility information needed to design a project and acquiring and managing that level of information. Again, here is a very important point. For every project and every stage of the project, you really do not need to go to quality level A. For example, if you are just in a initial pre-feasibility studies, even quality level D and C data gives you enough information for your pre-feasibility. But if you are going in construction and not going up to quality level A, well, that's where you're inviting trouble. So 4 quality levels, as we discussed, quality level D, C, B and A. Risks are highest if we are at the lowest level of quality levels. Risks are reducing as we go in the higher quality level, and of course the cost is going higher as we are going in the increasing level of quality. So quality level D is record research, recollections, as-built drawings. Very interesting point to note here. Generally, the people living in a particular area for a long time know a lot about the utilities which have been laid there in their lifetime. Now, till now there was no process where you can actually put this kind of information on record. Quality level D gives you the liberty of first of all doing the record research by your existing organizations, by various utility owners. You can take the data. Recollections, you can talk to people, find out about their memory of the utilities being there and put it in the drawing. As-built drawing is another source of it. We put this entire data together. So this is all the work which you can do to make a quality level D map. This is of course the least reliable information which is there. Then comes quality level C. In this process, you actually go to the site, pick up your surface appurtenances like manholes, walls, the electricity junction boxes, telephone junction boxes. Now you have these surface features mapped, so you can actually adjust your quality level D information with this surface feature information and make it more accurate. Then comes quality level B, where you use geophysical tools. There are different kind of geophysical tools: ground penetrating radar, induction locator, acoustic locator, etc., etc. Now we will look at few tools which are critical for doing a proper SUE, but it does not limit us because the technology is advancing day after day. New tools are coming in market. So idea is to use geophysical tools to actually locate, to designate rather, the utility as it is underground. And so geophysical tools, the first one which you saw was a GPR. This is a ground penetrating radar. It is sending electromagnetic impulses into the ground, getting you the utility information. The advantage is that GPR is able to locate both metallic and non-metallic utilities. Disadvantage is that it needs certain experience and expertise, not only to collect data but mostly to interpret data. Then you have induction locators. So these induction locators again are very useful tools. They can be used to detect mostly metallic pipelines and cables, but both of them, GPR and cable locator, complement each other in giving good data on underground utilities. Quality level A, it basically involves excavation at the location of the utility, so you are able to find out exact depth of the utility and note the vertical position. Sometimes it is not required to do vacuum excavation. You can actually open the existing chambers, manholes, and do this. For example, this photograph is a covered utility with this manhole. This support is staff for utility checking, having the tools. Now the chamber is opened. You can see a power cable, you can see a freshwater pipeline, you can see this is the open chamber, and then you can record the level of all the utilities here. So you are able to elevate the data from quality level B to quality level A. This is an example of a GPR record. This is 500 megahertz antenna showing penetration up to a depth of around 2.25 meters and clearly showing a hyperbola. This is a hyperbola and another flat interface. This can be related to slab or box drain. We will look more into GPR in a separate session on GPR, but the data needs to be processed and ultimately you are able to detect your different pipes and cables and structures underground. When we come to subsurface utility maps, they are to be prepared in strict adherence to SUE guidelines as ASC 3802. The most important point is that each and every utility which is there in the map has to be attributed a quality level based on the basis of their information collected and thus reflecting the confidence level in the utility information. This is the soul of the process of SUE. If you get a map which does not give the quality level on that particular map, that definitely is not a subsurface utility map. This is the most important thing. The maps to be prepared using specific utility symbols rather than colors, enabling their printing by standard black ink printers, eliminating the misreading errors in poor light conditions. These are the changes, or these are the modifications which have been made for a particular project requirement where these maps were to be consulted during the work in the night time. So it's always good that you make them in black and white with giving utility symbols, eliminating need to refer back to legends. This format also allows easy photocopying of drawings for distribution to field level personnel. The specific line times developed for utility should be standardized for all such projects, enabling data integration. So example line times, as you see here, www, that is for water, sewer, telecom, electric. You can have 10, 12, 15 of these type of line types developed. The advantage of this kind of line type instead of color map is then you are able to use them in the poor light conditions. The maps to be divided and suitably scaled for printing on A3 size sheets. It is very difficult sometimes to open big A0 size maps in the field and then consult them. So it's always good to have A3 size sheet. It's for easy to use in field, ease of photocopying and ease of printing on a standard blankjet printer. The map should be in a standard coordinate system. See, the point is when you are doing SUV at a large scale and if your maps are in local coordinate system, it becomes very difficult to integrate the data. So it's always good to use them in UTM coordinate system. Depth of all the utilities to be clearly marked along with utilities. Diameter of utilities further explored under QLA also should be marked with the detected utilities. Here I will also talk about another important issue, and that is about levels. Generally, the level should be related to the mean sea level, MSL, because if you are giving a utility of the utility depth only, tomorrow if the road is being recarpeted and let's say 0.5 meters is added on that particular road, your utility depth will change. But if you are giving the whole thing in RL related to MSL, then this problem doesn't happen. So these are legend examples from, this has been taken from ASC 3802, different kind of line types, different kind of symbols, abbreviations and notes. So quality level A data point indicated by symbol, CQLA supplement data from all additional utility information. All quality level A elevations are for the top of utility unless otherwise noted. All utilities depicted at quality level B unless indicated by dotted line code and labeled quality level C or D. This is one way of reducing the congestion on the map by using notes. For example, if you have got 10 utilities detected in a particular survey and 8 of them are at quality level B, rather than writing all of them as QLB, you can give this kind of note, and remaining 2 you can give as QLC or QLD, whatever way it suits. This is again an example of another map with notes, labeling, line code and symbol. QL delineation by notes, one example, all sanitary sewers are quality level C. That means the sewers have not been detected at quality level B, and whatever information is there is based on picking up the manholes using surface land surveying techniques. 6 gas 24 feet RT of center line center, this 11 is quality level D. That basically means that this data has been taken from the background information and there are no quality level A data. It means no excavation has been done in this area. So these kind of notes also supplement the information which otherwise have to be put in with every utility. The typical team structure of a SUV team: project manager ideally should be a geophysicist or a civil engineer. Then there should be someone to do the QC, which can be a civil engineer. Interpreter ideally should be a geophysicist. GPR operator can be a technician, a diploma technician. Induction locator ideally should be a diploma in electrical engineering. Land surveyor should be a diploma in surveying. CAD operator should be an experienced CAD user. Data collectors on the background information can be local. Reason is that the people who are local generally have better interpersonal skills in terms of language and interacting with different departments, so it's always good to have them locally. If the work is being done for SDD, there should be a diploma in SDD which helps people find out about how the maps can be read, and of course unskilled helpers. Since we discussed that quality level B using subsurface geophysical methods is a major advancement when it comes to utility detection, we'll spend some time on this. Any of a number of methods designed to utilize and interpret ambient or applied energy fields for the purpose of identifying properties of and structure within the earth. Such methods typically include variant of electromagnetic, magnetic, elastic wave, gravitational and chemical energies. They vary in effectiveness based on geology, backfill type and homogeneity, utility material type, method of jointing utility segments, utility condition, depth, soil moisture, other nearby buried objects, ground surface type and smoothness, ambient noise, ambient temperature, surface conditions, stray and or interfering energy fields, and equipment manufacturer's biases. This is the definition which has been provided for geophysical methods in the standards. When we talk about geophysics, the best way to understand geophysics is to compare it with medical imaging. On this screen you see medical images created by different kind of energy and fields. Here you have ultrasound, you have X-ray, you have CT scan, you have MRI. So different kind of waves can be and energies have been used to create images of what's inside the body. For example, here is ultrasonic waves which have been used, X-rays passing through the hand, more exposed wherever the density is less, blocked where the density is high, so creating an image of the subsurface, in this case body. Now compare these images with the images created using geophysics. Here for example you have a shear zone in a otherwise good bedrock using electrical ray city imaging. You have reinforcement bars in a concrete slab using ground penetrating radar. You have underground pipes under the layer of roads created by ground penetrating radar. You have a cavity in otherwise good sandstone created by electrical ray city imaging. You have fracture zones in a dam body created using seismic tomography. So again, using different kind of fields, energies, rays and waves, we have tried to see what is inside the earth. So just like in medical imaging, we were trying to see human body. In case of geophysics, we are using similar methods to find out what's inside the earth. However, job of a geophysicist is slightly more difficult than job of a doctor. Reason is very simple. There is something called a normal human body. For example, going back to this picture, we know that these are the joints which are there in a normal human body. If there was another one here, that could have been interpreted as a fracture. Whereas there is nothing called a normal earth. Earth changes every few meters. So the properties of earth changes every few meters, and there is nothing what we can call a normal earth. That's number one limitation. Number two, human body is available for inspection in 360 degree. For example, if you go for MRI, your entire body goes inside the tunnel. Waves can come from all the directions in 360 degrees and the imaging can be performed. On the other hand, in the case of earth, mostly we are working with only one surface, and from the surface the energy has to go, get reflected, refracted, diffracted, come back on the surface receivers, and ultimately we have to make an image. So these are the main limitations of geophysics as compared to medical imaging, and that's why the job of a geophysicist is much more difficult. Now, in general, different costs are involved with different equipment, different time and the training requirement. Decisions are domain of appropriate professionals and require a standard of care. Requires knowledge of earth, utility features and equipment capabilities. There are methods for search and trace, and again there are grid methods, interpolation and the spacing is involved. Various methods which come under geophysical domain are pipe and cable locators. There are differences based on frequency, power, connection methods. It's important to choose based on capabilities and differences. It's advisable to have a variety of frequencies. It works for metallic utilities, and in case of hollow utilities, a sonde can be inserted in the utility and can be used with pipe and cable locators. Range of frequency required is generally 50 Hz to 480 kHz. And it's a good method for right utilities under right condition. So this is a very popular method, pipe and cable locators, when it comes to SUE operations. Then you have terrain conductivity, which creates and measures eddy currents, not suitable in congested areas and urban areas, very limited or no scope in the projects of SUE. Resistivity measurements, impractical for utility mapping projects. Metal detectors, applicable for shallow manhole leads, wall box covers, etc. Results not easy to interpret in noisy urban conditions. You can understand a small nail which is very shallow will almost give the same kind of response as a much bigger metallic object at 1 meter depth. So their applicability becomes very limited except finding out the manhole covers. Ground penetrating radar is based on EM reflection. Electromagnetic energy is sent inside the ground. It is reflected from any interface across which there is a change in dielectric constant. There are different frequencies available for this which affect basically the depth and resolution. It can be used for both metallic and non-metallic utilities. Thumb rule for low conductivity soils, diameter in inches required for depth in feet. Example, a pipe 5 inches in diameter cannot be seen at 6 feet depth but can be seen at 4 feet depth. This is called a fit-inch relationship. It's a thumb rule to see up to what depth you can see a particular utility. Skill is more important in GPR. Sometimes we are not able to see the utility directly, but we are able to see the soil disturbances or wall of the trenches, the trench which has been opened to actually bury the utility inside. There are optical methods for sewer line correcting two walls, laser light from one wall to other, infrared methods only for typical high heat difference conditions, X-ray methods suitable for wall between floors, magnetic methods generally not applicable in urban areas, acoustic emission, same problem, microgravity not practical in urban setting, radiometric for radioactive compounds, chemical limited use like leaked gas detection, etc. So there are a number of methods, but which method is most appropriate for a particular project has to be left to the specialist. The SUE engineer's task is to advise project owner on potential effects on utilities, inform project owner on SUE, different levels of SUE and discuss cost and benefits of various levels, recommend a scope for utility investigation, discuss and recommend formatting of deliverables, discuss the sequence of acquiring various quality level data, prepare utility composite with quality levels, review data with utility owners, and recommend areas for quality level upgrades. For example, in a particular area, if a very critical structure or foundation is coming in an area of 50 meter by 50 meter, the remaining area can be left at quality level B, but at least in this particular area it has to be upgraded to quality level A. So this is the task of SUE engineer. Owner has to specify the scope of work, formatting, render assistance while dealing with utility owners, because when you have to collect the quality level D data, you need some kind of support from the SUE owner. Notify engineer of any suspected deficiencies discovered during construction. It will help the job of SUE engineer. The optimum solution in terms of geophysical tools world over, based on so many projects and experiences, has been ground penetrating radar, one of the critical component for quality level B data gathering, and induction locators. These two are indispensable tools. Other than that, of course, you have acoustic tools. You can use magnetic locators for manhole detection in case they have been buried by road layers, but these two are the minimum tools to be used in each SUE project when it comes to designating the utilities. So with this we come to the conclusion of this particular session, that SUE provides an answer to subsurface information needs and has already been implemented in large scale projects in India. The conditions prevailing in India do mandate certain modification in standard procedure. This applies to any country or any project where you are applying SUE. The prevailing conditions might require you to modify the standard procedures a bit. Various geophysical methods exist, yielding useful information of subsurface soil conditions, depth to rock, hardness of strata, depth to water table, presence of boulders, etc., which might be useful for SDD operation and should be considered at specific location in addition to standard SUE. This discussion is not part of this presentation, but fact is that for many operations other than underground utility information, we need about hardness of soil, presence of boulders, etc., and there are various methods like seismic diffraction for finding out bedrock level, electrical resistivity imaging for finding voids, for finding boulders, etc. All that can be integrated with SUE data to have a comprehensive coverage of subsurface of the subsurface. With this we come to the end of the session. I hope you enjoyed it. In the next session, we will be talking specifically on different quality levels. See you then.